Alright, let's talk about mechanical energy. In this course, grade 11 physics, the two most important types, or the most commonly talked about or used types of energies in this course, and we made a list of 9 or so different types of energy: sound, thermal, nuclear potential, chemical potential. But in this class, the two I'm interested in will be kinetic, the energy of a moving object, and gravitational potential. Okay. Why? I gave 3 reasons here. There are math formulas for each. Hooray, I get to ask you more problem-solving questions. They are closely related to the first 2 units, the unit on motion and the unit on forces. And they're also related to each other, because when I lift up of a box, it will have potential energy, and we use this symbol for potential energy, energy due to gravitational potential. When I lift up a box and drop it, it moves, and when something's moving, it's got kinetic energy, and I use a little EK. So these two things are related to each other. They're related to the first 2 units, and there's math formulas. So that's the reasons why I'm interested in those. Oh, and something I forgot to write here, and I'll squeeze it in right here. Mechanical energy is equal to EK plus EG. So if a question says, what's the mechanical energy of an object, I would have to find its kinetic energy, I'd find its potential energy, I'd add them together, and I'd report that as my answer. So what are the units of the quantity work? If you watched the last video on work, work is measured in joules. The units of energy also joules, so they are the same. Okay? Don't forget it. So when I do some work on a box, I lift it up over my head. Then how much potential energy should have? It should have the same amount of potential energy as the work that I just did on it. So it should have EG equal to the amount of work that you just did. It's not going to have more, for sure not more. It might have a little less friction or something like that. Not in the case that I just talked about picking up a box, there's no friction, but it should have EG equal to W if I'm looking at a frictionless environment. So let's drive some equations here. First for EG. Let's start with work equals force times distance, and I know that the formula for force is MA, so work seems to be equal here to MAD. When I'm dealing with gravitational potential energy, the acceleration, when I'm talking about gravity, the acceleration due to gravity is 9.8 meters per second squared, so I'm going to change this A to a G. Often when I'm talking about gravitational potential energy, distance maybe isn't the letter I'd be interested in. I lift something up 1 meter, I lift something up 2 meters. They would have different amounts of energy, but I wouldn't necessarily say that their distance is 1 meter or 2 meters. I would say that their height is 1 meter or 2 meters. So let's change that to MGH for height, and let's replace work with energy because they have the same units. So I'll write EG equals MGH. So how much potential energy does an object have? Gravitational potential energy an object have? I take its mass, I take 9.8, I take how high up in the air it is, I multiply them together, boom, I got my answer. Okay. Let's talk about EK. How do I find kinetic energy here? Let's start with the exact same formula. Let's make the very first change to be the same, MAD. Now, kinetic energy is all about the energy because something's moving. And moving, okay, A is in motion equations and D's are in motion equations. When something's moving, I'm more interested in having a V in the formula because as V goes up, I'm guessing that it should have more energy. So let's figure out a way to get rid of A and D and instead incorporate some V's. Well, I know that there's a formula that has an A and a D in it. It's VF squared equals VI squared plus 2AD. So I isolate for AD, I get AD equals VF squared minus VI squared all over 2. There it is right there. So I'm going to substitute this thing right here for this. And I'm going to get work equals M times VF squared minus VI squared all over 2. Now, there's an assumption we can make about the initial velocity of this object. Everything initially starts at rest. So if VI is 0, I get that work is equal to M over 2 times its velocity squared. And I'm going to change this, instead of work, I'm going to change it to EK. So EK is 1/2 mv squared. And right there is the formula to find the kinetic energy of any moving object. I take its mass times its velocity squared, I divide it by 2, there I have it. So these are the two formulas for kinetic and potential energy, and just a little intro as to why we use it. And remember that mechanical energy is adding kinetic